Hi, welcome back to Chem with Go. Today we're going to take a look at another example of naming ionic compounds, and we'll do a couple of different examples this time. One where we've got the formula already, and then explain why there needs to be a Roman numeral in the name, and then we'll actually take a look at a couple of another example where we're taking a look at a couple of ions that we're going to need to put together, and then actually name the compound itself, taking into account that there may be more than one possible positive charge or more than one possible oxidation number for the metal ion that needs to be involved in the ionic compound. So let's take a look at these two examples right here. And if we were just going to name this according to the rules that we've actually learned in class so far, the names of these compounds would be iron oxide. But see, now we have a problem because both of these will be called iron oxide. And we need to somehow distinguish between the two. So what's the difference between these guys? Okay, well, we need to actually kind of break this down or kind of deconstruct the ionic compound first. Now, from our previous video, you may think that this compound right here is actually iron 1 oxide, and that is actually incorrect. And the reason why is because if we break this apart, and let's say we didn't know what the charge of iron is in this compound, but we do know, and if we look at the periodic table, oxygen will form a 2 negative charge. Now, in order for this negative charge to be canceled out, okay, by this iron ion, the iron must have a 2 plus charge in order to be able to cancel that out. And if we do the crisscross method to come up with a name for this, we actually get this compound Fe2O2. And we talked about this in class. You can actually simplify that. If the subscripts happen to be the same, we can go ahead and try to simplify this to form FeO. So the actual name for this compound, the Roman numeral that needs to go in here, is actually iron 2. And the reason why is because that oxygen, when it forms an ion, forms oxide, which is an O2 minus charge. And in order to form this, we need to be able to have an iron ion that has a 2 positive charge to form something neutral at the end. Okay, so now let's take a look at this. Now that you understand that, let's try to break this apart. If we deconstruct this ionic compound right here, okay, we can see that the iron actually has a 3 plus charge. And we already know that oxygen has an O2 negative charge. And if we do the crisscross method again, we put that together, we get Fe. And this 2 shows up as a subscript, okay, over here. And then this 3 right here will show up as a subscript for the oxygen. So here's the O and then the 3. And there's our formula right there. So now the name of this compound has a Roman numeral 3 in between the two names of the ions. So one more time, this compound is known as iron 2 oxide, and this compound right here is known as iron 3 oxide. All right, let's come up with another example in another slide. Okay, so this time what we're going to do is take a look at a couple of ions, and we're going to go ahead and put the ionic compound together, and I'll give you two kind of different ways to take a look at this and form them. And we need to come up with a name for the compound using the Roman numerals again, because as you can see from these two examples, I have two possible oxidation states or two possible charges for lead. I have a lead 2, which is over here, and a lead 4. Alright, well now let's do the crisscross method. And what I mean by the crisscross method is this number shows up as a subscript for chlorine over here. And it's understood that this is a 1, and that 1 shows up as a subscript over here. So now if we write the formula, it's Pb, okay, 1, and it's understood that that's a 1, so I don't actually need to put that. And then a Cl with a 2. Now let's name the compound. Okay, so this, because lead has a 2 plus charge, and it has another one that's over here that's a 4 plus charge, we need to make sure that we name this as lead 2 chloride. Perfect. Alright, now let's take a look at another example. Okay, down here below, we notice that lead again has a different oxidation state. It's +4. So this number goes down here again. And this is understood to be a 1, and this number shows up as a subscript for lead. Okay, and then we get the formula Pb, Cl, or Pb1, and then Cl with a 4. And the name of this compound right here is known as lead 4 chloride. Alright. Now, another way to actually take a look at this, okay, if we take a look at the lead ion again, over here, the 2+ charge, okay, if that's a 2+ and my Cl is a 1-, I need 2 of the Cl minuses to cancel out the 2+ charge that is on this ion right here. So the lead needs 2 negatives from the Cl to put this together, and that's what you get in the formula. I have 1 lead and 2 chloride ions to form PbCl2. Alright, and then let's take a look at this one. If this is a 4+, I need 4 1- to be able to cancel out the 4+ charge. Well, I already know that chlorine again has 1 negative. Okay, so that means I have 2, 3, 4 Cl minuses. And so again, one more time, I need 4 of the 1- to cancel out the 4+. And that's the reason why when I take a look at this, I have 1 lead atom and 4 chloride ions to cancel it out. Alright? And you use the same sort of logic, regardless of whether or not it's a compound that has, more than one, a metal atom that has more than one possible positive state or oxidation state, or if it's just got one oxidation state. Let's say it's aluminum and it's +3. You use the same sort of logic. How many of these ions am I going to need in order to be able to form a neutral compound and cancel out the positives with the negatives? Alright, hopefully that was a good enough explanation for you guys to do these problems, and I'll talk to you guys soon.